because I claim now, if I look at this set, A of u minus A of v, delete A of v, what I'll get is precisely the vertex set of the path, of this area of the path. Right? Remember, I'm trying to sort of find an area of the path, so find a part of the graph where a particular area of my linkage is critical. So I claim if I look at this part of my graph, the part induced by AU minus AV, what I'll get is precisely the vertex set of this part of the linkage. Okay, so let's see why is that. Well, so it's true that this part is in A of u, delete A of v, and the rest of the linkage is. So now I just need to worry about other surface vertices. So here, real quick. So I have my path. Let's change the orientation. And I have two vertices, u and v, with that this is a changeover for v, this is a changeover for u. And now I'm worried that there is a surplus vertex which is in the out neighbors of u, but not in the out neighbors of v. Here, w is a surplus vertex. But then where is the changeover of w? So then we go here, because u is adjacent to w, the changeover of because u is adjacent to w, the changeover of w is this way, and because v is this way from the changeover of u, and because w is adjacent to v, the changeover of w is that way from the changeover of v. But then the changeover of w is somewhere here in the middle, and yet we said we chose u and v with changeover areas as close together as possible. Okay, so that's great. So that means if I take such u and v, and I look at this, what I'll get is precisely a graph where this part of the linkage is critical. Okay. So now do it many times, right? We found a way to do it once. Now take a sequence. Take as many surface vertices as you can, so that you don't nest any more changeover areas. And so I claim that by what we just saw, this part is his out neighbors, delete his out neighbors. This part is his out neighbors, delete his out neighbors, and so on. So I've almost told you how to deconstruct the linkage. There is just a little bit left, and the little bit is that I don't yet know, I cannot yet identify this part, and I cannot yet identify that part, right? Just the very start and the very end. Okay, so here's this picture again with the critical sets. So to get this start at the end, you just do it. You add two more vertices. I'll show you in a second how. So we had two new fake surface vertices. We call them x and y. So x is adjacent from everything, and y is adjacent to everything. Right? I mean, that's just a trick, and it just happens to work. Now, to be able to refer to it in the future, I want to define the changeover place for x and the changeover place for y. It sort of, has not much connection to the changeover places we had before. This is just a formal definition, so that I would have a uniform language for later. So I'll call the changeover of x, it's going to be the s's, and the changeover of y is going to be the t's. Right? Remember, changeover is a vector with k elements. So that's what we do. Okay. So now we're not far from being done. So now we are finally ready to deconstruct it. And the way we do it is as follows. We build an auxiliary graph. We build an auxiliary graph where the vertices are, so I want to try and build a graph. So just go back a little bit. So my goal is I want to find this sequence, actually. I want to find this sequence. I want to find a sequence where I have y and then a bunch of surface vertices as close with changeover places as close together as possible, and finally x. So I'm going to construct a graph where I can get the sequence easily. Okay, so the vertices of my graph are going to be, so first of all, I'll have x and the change of x and y and the change of y. But also I'll have all possible k+1 tuples that look like this, v and a possible changeover of v. So what's a possible changeover of v? Is that just a bunch of k edges? Right, so a typical vertex of my auxiliary graph is a k+1 tuple like this. It consists of a vertex and k edges. and I'll ask, I'll be pretending that they're all possible changeovers, but really it's not a good look. Okay, so this is the vertices. So now to the interesting bit, what are the edges? We remember the critical graph subroutine, right? That if I have a critical graph, then I can find the linkage. Okay? And like I said, I'll refer to this as a critical graph subroutine. So now I can tell you about the edges. Now I'll try and tell you slowly. Slowly about the edges. Okay, so I have two vertices in my auxiliary graph, where it's P and the change of P and Q is the change of Q. And now I need to tell you when they're adjacent to each other. So I want to say they're adjacent. So I definitely want to make them adjacent if, in fact, they're surface vertices for my path, and for my minimal linkage, and the changeover of P is before the changeover of Q. And that's my goal. That's what I want to do. Okay. So what I say is, I need for these conditions to be true, I need that P is adjacent to Q. I need that the out neighbors of Q are a subset of the out neighbors of P. And I need, so I look at this graph, I look at the out neighbors of P, delete the out neighbors of Q. Right, so here it is. And then I'll try and run my critical graph subroutine on these pairs of turbulence. Right, so it has this changeover points. I can say this is left, this is right. And then I'll try and run my critical graph subroutine on the pairs that consist of the left end, the right end of the changeover place for Q and the left end of the changeover place for Q. And I make the green vertex adjacent to the purple vertex if 1 is true, 2 is true, and also